so it's really close to the mountains, good skiing. So it's a really neat location. It's a school primarily for physical science and engineering, so it's about 4,000 undergrads, another 1,500 grad students. It's pretty competitive, so there's generally about this 13,000 applications for just 950 students in the freshman class. And if you want to know any more information about School of Mines, you can ask Max Robb here, who's an ore digger, Colorado School of Mines ore digger graduate, as I just learned today. So there's a ore digger amongst us here, which is great. So the other part is NREL, and so NREL is also in Golden. It's only 3 miles away from School of Mines, so I'm going there quite a bit on my bike. So it's neat to have that resource close by. So it's also a big organization of 2,500 people on a big campus with state-of-the-art equipment, a DOE lab, and so most of you know it's a world leader in renewable energy. They have the National Center for Photovoltaics, for wind technology, and a nice annual budget. And I just got the email that if this shutdown goes any longer, it might really affect NREL. So they have about a 25-day buffer before bad things start to happen. So this is actually affecting DOE labs. So again, I'm preaching to the choir, so maybe I don't need to talk too much about the advantages of organic solar, but low-cost materials. So this is, of course, copper phthalocyanine. It's an active material that can be used in organic solar. It's also a blue pigment that can be used in car paint, and so it's in paint exposed to sunshine, hot and cold temperatures, so they're relatively stable materials. You can conceivably think about this as a roll-to-roll process, so really low-cost manufacturing and low-cost installation. So you can also think about rolling this out onto roofs, and so no need for framing or any type of things like that. So lightweight, flexible. And then, more interestingly, you can see that if you look at the slope of how the efficiencies have gone over the past 10 or 15 years, it's been quite a sharp slope. So this is a function of more money coming in, more people jumping in, people learning from each other. But this is a pretty sharp slope, and more recently, some of the tandem organics can get up to 10, 11, 12%, which is of course a huge jump from just 6 or 7 years ago. The other thing is that not only efficiency, but some of the groups, especially traditional silicon and SIGs and CAD-TEL people, are always worried about lifetimes of OPVs, but there's been some academic work done at Stanford from a McGee group showing that in particular bulk heterojunction systems, you can get extrapolated lifetimes out to 4, 5, 6 years, and this is already a couple-year-old study, so I'm sure that these numbers are even higher. And Heliotech is a company that is kind of a spin-off of BASF and Bosch in Germany, and they have a study that shows 30-year lifetimes. And so as long as you do proper encapsulation, you shield these from water and oxygen, I think they'll do quite fine in terms of lifetimes. So then if you look at how solar cells are rated, you basically have a calibrated light source, normal incidence 25 degrees, so if you think about it, that's not really solar cell operating conditions. The solar cell is going to be sitting outside, it's going to be light from different angles, and it's not going to be always one sun, and so it turns out that OPVs actually do much better than silicon at low angles at varying temperatures, and so you can conceivably think about getting 30% more efficiency out of an OPV at real operating conditions versus traditional silicon. So you can think about a 10% OPV cell may behave more like a 13% rated silicon cell. This is just something that I thought I would introduce to you guys in case you don't know. And the other thing is that, OLEDs are kind of the precursor to OPVs. And I would argue that the fact that we have, OLED displays in our pocket that we can now use this is a lot harder technology, in my opinion, to end up in consumers' pocket than a solar cell, because if I'm looking at this with, how many hundreds of thousands of pixels, and one of these pixels goes out in the middle, then I'm going to go back and want to get my money back, Whereas if this is a pixel in a solar cell, it's just going to be negligible noise, So the fact that this is a technology that has some kind of aspect where the consumer is looking at it, and these are able to be produced at mass volumes, especially the smaller size displays. When you're talking about the larger size displays, these are, of course, a little bit more expensive, and it's taken a bit longer to get to the marketplace, but I think it's coming. And now I think, this is one of these flexible LG displays that I think are going to be sold in the next couple of weeks or something. So, so the fact that this is out there and available is very promising, again, for organic PV. And so, there's big calls in DOE for funding for OLED lighting. So this is another big part of this organic semiconductor technology. You can have these transparent displays or transparent substrates, so you can create light from a transparent window. And then, solar cells, these are all the typical, the Konarka slide, roll-to-roll, dye-sensitized solar, so you can have solar cells, different colors. You can even take your kid to the country for a nice hike in the woods, and he can park himself and play the Game Boy, just like they always do. So in any case, this is just to paint a nice picture that I think this is a real technology. It has extreme potential, and there's a lot of reasons why it should work. And, of course, if you think about it, there's been 3 Nobel Prizes associated with this technology. So the original fullerene discovery, 1996 Nobel Prize, the Heger conductive polymers, and then the last one in 2010 was for the carbon-carbon bond formation. So this is quite interesting how all of these technologies sort of converged on all of these organic semiconductor technologies. So if you look, as I alluded to earlier, at materials used in organic solar cells, they can sort of be classified in electron donating materials and electron accepting materials. And, I didn't quantify this, but I would estimate that about 90% of all the synthesis-related publications are on the donor side. And that's been a lot of where the progress has come in the efficiencies, have been in all of the improvements in the donors part of this technology. And relatively fewer papers, although more recently there's been a lot more papers coming out in this area. There's been primarily work on fullerene derivatives, some cyanoaromatics, but relatively unexplored. So when I started thinking about getting into this area, this was for me a bottleneck where I could conceivably come in and make some progress. So, one of the things about fullerenes is that they really don't absorb a significant amount of the solar spectrum. So in the device, they may not be participating a lot in the photocurrent aspect. And so this is an example of the C60 fullerene and C70 compared to another acceptor where it has a much higher absorption coefficient. And then if you look at the VOC, which can sometimes be described as the difference in the HOMO of the donor to the LUMO of the acceptor. And so conceivably, if you had a new acceptor, you could push this higher, and this value for VOC could go higher. But of course, that's not the only thing that affects VOC, but it's one thing that you could possibly tune in a higher VOC by working on these materials. And the last thing is that they're actually pretty hard to make and to purify, and the cost, even after fullerene derivatives being around for so long, are still quite expensive. And so there's been some studies that show that 10% of the total cost of the OPV system can be attributed to fullerenes. And so this can be a little bit worrisome when you think about that. So there's a study here in this Environmental Science and Technology, which I think it's pretty interesting. They look at the cost associated with the whole production of fullerenes, and so they even put a cost associated with the soot So you can make soot, and then you can go into the soot and you can extract out the fullerene mix, and then from there you have to separate the C60 from the C70, and so these are all costs associated with that, you know. And then to get from 95 to 98% purity, there's another cost, and then you have to take the naked fullerene and to derivatize it in order to be soluble. So, you know, these are all high costs associated with this process. So there's, you know, chromatography, all kinds of things that you need to do to purify these. So, and you'll also see from the examples that most of the recent record efficiencies are coming from the C70 derivative that you can see is 3 to 4 times more expensive than the C60 analog. So, you know, this is kind of looking at the module cost, so you can make some assumptions about module efficiency of 10%, active layer thickness of 200 nanometers, volume fraction of the acceptor 50%, and you can see that in the end, the cost associated with the fullerene is significant, and it really cannot be ignored. So you can see, you know, I'm building this up to where we enter this equation. So, you know, I'm just going into the literature and I'm trying to find the highest efficiency examples that I know about, and so I think these are some of the high numbers. So there's a 9.2% efficiency single cell device from the Sao group in China, inverted cell. Of course, our buddy down the road in UCLA has done some nice tandem cell work and is up to 10.5%, 11%. And then my buddy in the front row here has done some really cool work on making a sort of all small molecule solution process device. And sorry if that number is higher than 7.8 now. I'm not able to keep up with the progress. Yeah. On some days it's higher than 7.8%. So anyway, you know, this is all, like I said, you know, these are numbers that are approaching, you know, something really interesting that I think all of the silicon SIGs people are really, you know, starting to pay attention to. So all of the record cells use fullerenes, and mostly they're using C70 and ICBA, which are some of the more expensive fullerene derivatives. And all of the more recent developments in this area are on the donor materials discovery side. So we got into this area, and one of the first things that I wanted to do, you know, especially because I had this 5 years of industrial experience, you know, I wanted to do everything inexpensive, minimal steps, you know, inexpensive starting materials. And so in the University of Michigan, I had come across these dicyanoimidazole structures, and so the professor there, Professor Rasmussen, was using these to polymerize these vinyl groups with methacrylates and styrenes, and he was trying to make high nitrogen containing polymers for low flammability to use in the casing of wires for airplanes to make, you know, less flammable materials. And you know, and then when I started to look further into this, turns out that these were, you know, quite commonly used as fertilizers, and they were a lot of patents by Monsanto in the early 50s and stuff. But you know, from a chemist's perspective, these are really electron deficient molecules. There's 2 cyano groups. There's a imine here, and then there's a place here where you can think about alkylating for solubility, and then for the vinyl group, you know, it may not be that we need to polymerize that, but we can do some of the heck chemistry. So I contacted that professor, and of course he has a company, and he was willing to sell me some of this stuff, and so I bought it. And this is work that we started in Singapore, and so we had this monomer that we bought, and then we can alkylate it, and so we can make all kinds of these derivatives in very high yield. Then we can go into Aldrich and look at all the different types of bromoaromatics, and we can start doing Heck reactions. And so we didn't know if this was going to work at first, and it took a while for us to come with these conditions to make this a high yield reaction. So we published this back in 2009 in JOC, and so we looked at all these derivatives and, you know, did all of the band gaps and absorption and PL, and found out the best candidates for these to use with P3HT in solar cells. And so you can see that these molecules are absorbing quite strongly in the visible spectrum, and they're really fluorescing quite high as well. So we even made some OLEDs out of these, and they actually work pretty well. So so one of the candidates, of course, like the way it always seems to turn out, is this benzothiazole. This is always the best acceptor moiety in organic PV for some reason, and so that was the molecule that ended up working the best. And so you can see that we also had a good team of chemists and device physicists, so working in the same lab. And so we made the hexyl derivative, and it turned out that the hexyl was not so soluble. So then, of course, we just went back and made the ethyl hexyl, better solubility. And so there's conjugated link. This is completely planar. There's ability to solubilize, and they're absorbing quite strongly. They have really large extinction coefficients, so they could contribute a lot to the photocurrent. And they can be sublimed, and so you could conceivably make all vacuum deposited devices. So we made these, just solution processed devices, spin coat, and we were operating sort of in the first devices that we made were this was probably in 08, 07 time period, and I had a postdoc in my group who had worked in OPVs for a while. And we started making like 0.3% devices, and I was demoralized. This is like awful. And this postdoc was so excited. He's like, I cannot believe it. We actually got like an efficiency from a non-fullerene acceptor. So I said, okay, I'm glad you're excited. Let's keep going. And so we kept working on this, and then we maxed out in Singapore about 0.8, 0.7%, and then we went to Stanford and we took it and started combining it with some Frichet polymers, and we knocked it up to about 1.4%. And you can see, the interesting thing is that this peak is associated with the acceptor, and this peak is associated with the P3HT. So we're actually getting most of the photocurrent from the acceptor, so it's contributing a lot to the photocurrent, which was nice. And the other thing was that we're getting a slightly higher voltage out here, a little bit, 0.6 than fullerenes, but not too much higher. So that that aspect wasn't really working out at that time. So then we started to think, well, how can we make these better? And one of the things that we recognized was that the mobility of these materials was an order of magnitude lower than the corresponding donor. So we thought that there may be some bottleneck there of extracting charges. And from a chemist standpoint, we're looking at this molecule and we're thinking, well, maybe it's because these solubilizing group are in this kind of strange part of the molecule, and what if we put the solubilizing group out here and made a more symmetrical monomer? And so that's basically what we did, just a simple chemist intuition kind of procedure. And we made these guys. So we kept the benzothiazole moiety, and then we just started working with these phenylimides and these naphthyl imides, and started to push forward. And we had some help early on at Stanford from the Burdagh group at Georgia Tech, and so they were helping us to look at these. And so these are completely planar, and they have a nice distribution of HOMO LUMO levels. And if we compare the two, when we have this phenyl imide, you can see it's completely planar. When we have this naphthyl imide, there's a little bit of a twist here. And I'll come back to that in a second. So the question here is, does that make a difference? And as you'll see, it makes a huge difference. So the chemistry that we set out in the beginning was pretty simple. We were just using vinyl silanes and making these vinyl silane derivatives, and then doing these coupling reactions in the presence of fluoride. And so the fluoride will kick off the silicon and make the divinyl in situ. And so we can do that for both with pretty decent yields. Then, of course, I had a new postdoc that came into the project, and he didn't like that procedure, and so he used this procedure, which is, again, using a vinyl boronate salt, and he pushed up the efficiencies even higher. And so now, we're operating in this from materials that you can basically buy from Aldrich to the end molecule, like 70% total yield. so we don't have to go through that enormous process like you did through fullerenes. And so that's one of the keys about this, was being able to do this and get high yields in very few steps. So, we started to compare these two acceptors to one another, and, they're pretty similar. They have similar absorption. The energy levels are pretty similar. And so we thought, of course, naively, that these would perform the same. But it turns out that when we started, so first thing we wanted to do was, so I know that when you look at FET mobilities, it's not a really good way to look at mobilities for solar cells, because this is more like a lateral mobility, when in a solar cell you're looking at vertical mobility. But in any case, this material had a order of magnitude higher FET mobility than the dicyanoimidazole structures that I talked about earlier. And we couldn't even measure an FET mobility for the material that had the twist. And so this was work done by a grad student in Alberto's group at Stanford. So this was good, because now we're sort of on the FET mobility side of things. We're on the same order of magnitude with PCBM. So we thought that's good. And we started making, some of the first devices. And, we got about 2.5%, and this is what we reported in Chemistry of Materials a couple years ago. But the corresponding molecule with the twist, you can see, is basically 10 times lower. So just that little bit of twist, is really affecting how these materials perform in the solar cell. So the one thing that you'll immediately notice is that we can jump up the VOC from a fullerene device that's usually about 0.6, almost to a full volt for these. So that ability to adjust the LUMO is quite important. And again, this twisted molecule is 10 times lower, and so I'll show you a little bit why that is. So this was some of the first, stuff that we did. Then we've recently pushed that 2.5% all the way to 3.7, and some of that is because we've actually switched our source of P3HT. So P3HT that you can buy from Aldrich or from Reiki is a certain regioregularity and a certain purity. But I got my buddies at BASF, and so they, kind of slip it under the table to us, and they're making kilograms at a time, and so they just gave us 10 grams to play with, and this was a big difference. You can see we get a lot more, current out of the device. The fill factors are much better, and it corresponds to a much better efficiency. And we've also been working with another thiophene backbone polymer from Jinan Bao's group, and you can see with that one, we can get up to a full 1.1 VOC just in a single cell device. And so I think that's pretty interesting. And so we've been kind of plugging away through this, and again, this non-planar naphthyl imide is still operating in this sort of 0.2% range. So, this is, I think, one of the highest non-fullerene OPVs to date. Of course, when I was preparing for this talk, I went to see what is the recent progress, and, was demoralized to find that there's at least 3 ASAP papers that are up around 4% now. So that's why I had to switch to the highest to one of the highest now. But it's good, because I think that, everybody's jumping in, and the more people, the better, The other thing is that this student, Jason Bloking, at the MRS meeting last spring, he gave a poster, and our poster was so popular. Everybody was crowding around, and then there was like a Sigma Aldrich guy that was walking around, and he saw this excitement, and so he came. And so now, Sigma wants to help us scale this up and try to, because we want to get this into as many people's hands as possible, because we're just a small group. We can only do so much, but we think that if our acceptor can get into other people's hands, then this number can be pushed even higher. So hopefully we can get this stuff scaled up, and I'll be giving it out to whoever I can to work on this. So again, with this system, we're also getting a significant part of the photocurrent coming from the acceptor. So this is the acceptor contribution, and this is the P3HT contribution. And then if we look at the the grazing incidence angle, we can see that if we compare this original phenyl imide that's planar to this naphthyl imide that's twisted, you can see that there's a huge difference. So this stuff will not crystallize at all. We don't see any diffraction peaks on the outside. And so, just looking at these qualitatively, you can see that there's a big difference, and we think this translates to the ultimate device performance. And then if we go further and we start looking at how the this planar HIBT along with P3HT, you can look at just P3HT by itself, and there's still some peaks associated with the P3HT, but there's also additional peaks coming in from the HPIBT. And in this other case, you can see there's really no contribution from this twisted naphthyl benzothiazole. So, this is good because we can see that there is still some crystallinity associated with the with this planar acceptor, but you can see it might be bad because it means that it may not be miscible at all with the polymer, so it's just kind of phase separating on its own. And that may be a problem for getting charges out of the device if we can't control the size of those domains. So, this goes back to, of course, this work was initiated in the McGee group, and so they've done a lot of work in trying to explain why fullerenes work so well. And they've published a few papers on, how these fullerenes can be, basically solubilized in the side chains of certain polymers, and how, they think that there is a mixed phase where the fullerenes can be more soluble in these mixed phases, and of course they cannot be solubilized in these crystalline domains of the polymer. And so if you anneal it, it sort of kicks these fullerenes out of these mixed phases, and they sort of kind of segregate out. And so, in the non-annealed device, you can see that everything is much better. When you anneal it, in this case, everything gets worse because you start to create these isolated domains and you can't get the charges out. So we think that may be an issue with our system. So they've been pushing a lot about this theory of a three-phase system where you have this, basically you have a possible domain where it's just the acceptor, and then the mixed domain may have a different band gap. The same thing with the P3HT, and so everything is sort of happening in this mixed domain. So that's one way to think about this. And in our case, you can see that if you look at just the P3HT by itself, and you start to incorporate our acceptor, you can start to see evidence of crystallization at really low percentages. So what we're thinking is that this acceptor is not soluble at all in P3HT, and maybe that's a problem. And so this of course helps us because then that means that maybe we should be designing materials that could be more compatible with P3HT, so we could help to make more of these mixed domains that may help to get charges out of the device. And so this is kind of recent work in trying to figure out how to go further based on all this new data. So yeah, there may be a miscibility limit of this particular acceptor in P3HT, and also the same is true for the polymer from the Bow group, where you can see that immediately at 5% you start to see these rings associated with the acceptor. And so we're starting, this may be an issue that we need to address going forward in order to see if we can push these efficiencies higher. So they even looked at regio-random P3HT, and so this stuff is not even soluble at all in regio-random, so immediately you can see the stuff starts to crystallize out. So these acceptors really like each other, and they want to kind of hang out with each other, so we need to figure out a way to break that up. So here's the original acceptor that we've done, and I've been meeting you guys throughout the day, and we found we have examples where we've swapped out this benzothiazole with other moieties, and everything dies. We can't even get any efficiency out of the device. So it seems like this benzothiazole is really important, And so now, we've made a series of derivatives, and we're starting to test those. We've made this vinyl group in imine. We've put fluoro groups. We've made cyanoesters. We've made rhodonines. And so, all of these molecules are, planar, and they all kind of fulfill all of the initial hurdles that you need to do in terms of band gaps and LUMOs and stuff. And so it all looks promising, but of course, as we all know, it's not that simple. Everything looks great, and then you make a device, and that's kind of where you roll the dice. So this is kind of where we're at. We've done some, the group at NREL, Ross Larson and his postdoc Travis Kemper, they've done some modeling of, in this case, the cyanoester. So these, again, have nice LUMOs. They have, similar band gaps like the acceptor that works well. These rhodonines also look pretty good in terms of the LUMO levels. We like to keep these around 3.4, 3.5. So, they're all passing the initial hurdles, and so now we're starting to make devices with these. So yeah, this is when we're looking. So we're at 3.7, and so I started looking around, and so here's a paper in Advanced Materials ASAP. They're at 4% with this kind of, bis imide that's kind of hooked together at this bay position, and I don't know how they're getting it to be exactly in that particular bay position, because who knows if it's, so it's kind of interesting, and I would argue that, I don't know if that's much easier to make than fullerene. I didn't go into the device synthetic procedure to see exactly how hard that was, but it, it's interesting. They're at 4%. There's this other paper by a Japanese group that are using this quinoxylene with this basically I think it's polyera, this polymer acceptor that polyera has that you can buy, and they're up to 4.1%. And I think in the same issue, Antonio Facchetti had a 2.7% device with this acceptor, which I thought was interesting because I thought that they had been reporting like 5 or 6% in some of their meetings, so I don't know why they're publishing on 2.7. But in any case, so
It's a different compound.
Yeah, it could be. I don't know. They're probably holding out for that 6% result for later. But in any case, I think 4.1 is the highest I could find. And then Sam Janicki just reported in JAX this all-polymer device. And this is, again, kind of a polyera type structure, except for they're using a selenophene here. And they're up to 3.3%. And then there's this compound that came out in Chemical Communications with P3HT at 2.9. So, so again, it seems to be this 3.5 to 4%, which is about half of what you can get with the fullerenes. And so, is this going to go higher? I don't know, hopefully, but we'll keep going. Again, the amount of work that's being done in this area is negligible compared to what's being done on the donor side. So I think, again, as more and more people jump in, this is going to push these numbers much higher. So usually, it's the case where you have lower JSC and lower fill factor than the corresponding fullerenes. All right, so I think I'll move on to this ternary system. This is work that we kind of stumbled upon. So we had been making low band gap dyes for dye-sensitized solar cells. And it turned out that one of the byproducts of this process, actually the chemist who did this was Bogyu Lim. He was actually here as a postdoc with Fred Woodle, and then he came to my group at Stanford. And so he, had this material, and he just gave it to the grad student and said, just sprinkle a little bit into your PCBM P3HT, and it's incredible what happened, and I'll show you. But it was just one of these things where, again, the ability from the chemist and the device people to kind of hang out and be able to just be open to try new things. So, so we did that, and we got this great result, and then we started looking if anybody had done it in the past. And so there was a couple of papers, again, by this a group in Japan, where they take a couple of these phthalocyanines. And so this is a zinc phthalocyanine where they add some solubilizing group on the periphery. Or you can do these silicon phthalocyanines where you add the solubilizing group at the central silicon. So this is basically coming out of the board, and this is going into the board. And so you can see, that they make these devices and they can get a little bit more photocurrent out here. And so they translate that to a 2.2% device, and then adding this dye, you can push it up to 2.7. So this was one of the first examples that we found for this. Then, there's another paper that came out earlier this year in Nature Photonics where they use a squarane dye, and they're also able to get this little bit extra photocurrent out here, and that somehow pushes the efficiency from 3.3 all the way to 4.5%. So that's quite interesting. So here's what we did. So we made this naphthalocyanine derivative, and so in the case for the dye sensitized solar cell, we had one of these groups that was acid, and that acid would be hooked onto the titania. But this was a byproduct, and so the chemist kept getting, like 50% byproduct, and he just got to do something with this, and so this is what he gave to the device guy to sprinkle in, the magic dust. And so you can see that these, are really redshifted almost out to 800. They're really soluble because you can, basically tune this big group out here, and the extinction coefficient is 2 times higher than the corresponding phthalocyanine, so you can not only redshift, but you can really increase the absorption. So, the synthesis is, not easy, but it's, it's not that hard. In fact, you can buy this, but Bogu made like, 50 grams, and so he just wanted to start from scratch. So each process is, pretty simple. We had a problem at Stanford of using anhydrous ammonia. So it would have been like a bunch of, paperwork stacked like this much to get ammonia in there. So we actually found a company close by, and they charged us a couple $100. So we just gave them the precursor, and they did it, and gave us back like 10 grams of this compound. And so that was easy. So yeah, we could make the corresponding silanol, and then we just cap it with the chlorosilane, and so we can get this relatively easily. And so this is Bogi that did all this work. He's now in LG in Korea. So, if you look at the absorption, so here's the absorption for PCBM, here's the absorption for P3HT, and this is this silicon naphthalocyanine, so again out to almost 800. So then if you look at the devices, so Jason Bloking, the same student that was doing all the acceptor work, he was doing all this stuff on the side. He was tracking the amount of, this is weight percent, compared, this is like based on solids. This is compared to the P3HT PCBM weight percent. So, looking at incorporating this dye in certain amounts, and you can see, we start off at 3.8%, and we can push this all the way up to 4.5%, and our champion device is close to 5%. And so here, this is the IV curve. The amount of current that's coming out of the device is quite high. So the cool thing is that if you look at the EQE spectrum, I mean, we're getting like a huge amount of photocurrent out here, and we're really not taking much of a hit on the EQE on the P3HT side. And when we anneal this, it gets even better, and we get this extra peak that forms out at 830. So, I mean, it's really, we're trying to figure out exactly what's going on here. So we're getting, all of this extra photocurrent, and here after annealing, it's actually improving the EQE out here. And the other thing that's interesting is that you can buy this naphthalocyanine without Tbutyl groups. And so here, in our case, we made these with Tbutyl groups. Without the Tbutyl groups, you don't get that much photocurrent, and you don't see that extra peak out here associated with annealing, whether it's due to some aggregation. So again, we're wondering, if this is again related to this mixed phase. Is this extra bit of solubility from the periphery enough to get this into the mixed phase in order to get all this extra bit of photocurrent out, whereas in this case, we're just getting a little bit out. So, I mean, this is all just kind of recent stuff, and we're just putting the manuscript together. So, we're thinking that this must be fitting right in the sweet spot here, and we're able to, because traditionally if you put a low bandgap dye in the system, all the energy will just get funneled to that, and you basically lose all the other, good contribution to your device. But in this case, it seems to be complementary, and so we're able to get all this extra photocurrent out in these infrared areas. So, we're trying to figure out exactly what's going on. We've made systems where we just incorporate the dye with P3HT, and we don't see that aggregation peak. We incorporate it just with the PCBM, and we don't see that aggregation peak. So it's this ternary system that's helping to produce this extra aggregation peak that's giving us that extra photocurrent. So, here, if we look at, without dye, incorporating the dye with Tbutyl groups, we're starting to see a little bit of stuff happening out here. I'm sorry. So this is with the Tbutyl group, so everything sort of stays the same. So if we go to P3HT, we add the dye, we can see that there's not much going on. But without the Tbutyl groups, you can see that there's all these extra peaks. So it's definitely aggregating out, and it's not soluble. And in the annealed system, it's even worse. But in the annealed system with the Tbutyl groups, you can see it's not, you really can't see too much extra happening. So it must be, staying soluble in some neat part of the bulk heterojunction. So yeah, that's it. I mean, we've, the conclusions are that I think this is very interdisciplinary, and having chemists and device physicists and computation people all kind of hanging out together is really important. And I've been able to work together with School of Mines people in the physics department and materials and ChemEng, and working together with Michael here and with Sean Shaheen, who just recently moved to CU Boulder. So our kind of strategy is to look at attacking bottlenecks by using simple high yield chemistry. So here's acknowledgments. These are all the people that contributed, the funding sources. So KAUST was involved early on in the process. We're doing some work now in the MERSEC at Colorado School of Mines. And so these are, Jason did the early work, and now Dave Ostrowski is a new postdoc doing work on the devices. And these are all the chemists that have contributed throughout the process. And I think, so there's Bogu. I don't know, remember that guy walking around the hallways? So he came up to my group, and this is Tommaso, and then this is Unsal. They did a lot of the chemistry on this project. So I think that's it. Is it? Oh, I wanted to quickly show you some of the stuff that we're doing now on some other projects. So we're working on silicon quantum dots, and we've been able to show, so if this is a, computation of a silicon quantum dot looking at HOMO LUMO levels, everything is sort of confined within the dot. And when we can derivatize these surfaces with certain groups, you can see that we can totally shift the HOMO out to the periphery and keep the LUMO on the inside of the dot. And the important thing is that we keep this double bond. So we have a double bond that's connecting the aromatic ring into the silicon quantum dot. And so it's showing that this is, everything is communicating there. And when we get rid of that and just make a single bond here, then, there's a little bit lost. And so it really changes the band gap quite a bit just by making this simple chemical change. And so that's kind of the stuff that we've been working on, some of the new stuff that we've been working on at CSM together with Mark Lusk. And so, Lust, sorry. I'll have to switch that. Yeah, that's right. All right, so that's it. Thanks for sticking around.
I'm sure there's some questions from the audience.
Do you have any idea how much cheaper some of your acceptors are compared to fullerenes? And do you have any comments on how much cheaper they need to be?
No, we haven't done a cost analysis yet, but based on the acceptor that I showed that got the most efficient devices, I think benzothiazole is pretty cheap. And then we start off with that bromo, phenyl, anhydride, and that's like really cheap. So, yeah, we probably should go through some thorough cost analysis and come up with some prices and see.
Your efficiencies may be half, but I would guess that your costs are more than twice as cheap, right?
Yeah. So, yeah, we're not happy with these efficiencies. We don't think that anybody is going to be excited about those efficiencies. So, yeah, assuming that we can push this higher. But yeah, you're right. We should do some kind of cost analysis on. So I shouldn't be, starting off my talk bashing fullerenes and then not provide any information about where ours stack up.
Well, I think it's optimistic.
Yeah. No, I think so too.
Have you started exploring any polymers like donor materials with that narrower band gap as well? Because there seems to be kind of substantial overlap.
Yeah, so every time we deviate from a backbone that is all like thiophene based, the efficiencies sort of crash. So anytime there's like a donor acceptor polymer, things don't work out. And so we haven't explored that fully. So, so a lot of for PCD, DBT, all of these polymers that are getting 7, 8, 9% with fullerenes, when we try them, it's pretty bad. Some of it is because our LUMO level is like 3.5, so there may be some problem in the LUMO. But we did get one of those low band gap polymers from Yang that he claims has a LUMO about 3.2, like similar to P3HT, and we couldn't get that to work. We tried a looping U polymer, it didn't really work. Some Leclerc polymers. So far, our best results have come with all thiophene backbone polymers. And so we're kind of trying to figure that out as well.
More questions?
Yeah.
Have you looked at the PL quenching efficiency? They're more efficient.
Yeah, I didn't show it, but they're quenching quite strongly. And in the case of the bow polymer, they really we're not able to fully quench the PL. I think it's because they're just so immiscible in each other, so we're always left with some domains that are photoluminescing.
So do you think the reason the current is still low is mostly because you have exotons to get to the interface, but then they don't split efficiently?
Yeah, I mean, we've done some work in that area, but I'm not confident enough to talk about it in terms of what's actually going on. But yeah, we do think that there may be some issues with getting the exciton to dissociate. But yeah, it's kind of early stages. I'm trying to figure out exactly what's limiting the efficiency.
More questions in the audience? So I guess I have a question. So with the silicon you showed,
Yeah.
have you looked at energy transfer there? I mean, it's interesting that you have you got something right in the sweet spot. So I think that P3HT, and I'm not sure the fullerene's quite the right spot to do have energy transfer competing with generation.
So the
emission of P3HT overlaps where you have.
Oh yeah.
I mean, it might be hard to tell. I'm just wondering.
Yeah, there may be some contribution. I think Jason did look at that. I haven't seen that results. But yeah, I mean, just if when you look at a traditional P3HT PCBM solar cell, they kind of have that burgundy color. Just with a tiny bit of the stuff, they completely turn dark blue. But yeah, there might be some transfer there. Yeah.
Any other questions for now?
What about the stability of your compounds? For example, air?
Yeah, I mean, so far, the devices that we make, we test in the glove box, and as long as we haven't encapsulated them and taken them out, but they still are operating after weeks in the glove box. We don't anticipate there being much of a problem there. I mean, we're starting to make inverted devices at NREL as well, and they seem to be getting there, but still not up at this high threes yet. But we don't anticipate. I mean, they're we keep them in open air. We're weighing them in open air and things, and they seem to be pretty stable. Those silicon naphthalocyanines, they may have some issues. I think we're still trying to study those. We sometimes see some precipitation, in solution, so we don't know if that's an aggregating effect or if things are decomposing.
Have you looked at those films by TM or any idea of how the three phases?
No, we haven't really done that. No, we've just done some of the X-ray studies, and I mean, this is all, this was all kind of a side project for this student, and he was trying to graduate. So, so I really am thankful that he generated all this data before he got out, because it wasn't his main project. He didn't even use any of this in his thesis, I think.
Any more questions for Alan? If not, let's thank him again.
All right, thank you. Thanks.